Bismillahirrahmanirrahim. Assalamu alaikum. Lecture number 6. The contents of this video lecture are additive identity for the set of a complex number. You know that this C is the representation for the set of a complex number. So we will define the additive identity in the set of a complex number. Then additive inverses for each Z in C. Z means any complex number, C is the set of a complex number. So remember that additive identity is always unique. Additive identity for the set of a complex number is always a unique. There must be a single number which will be used as a additive identity, but additive inverses are infinite, mean for each number there must be a different additive inverse. For every number there is its own additive inverse. So additive inverses are infinite, but additive identity is always unique. Similarly, the next content of this video lecture is multiplicative identity. NC means the set of complex number. So remember that multiplicative identity is also a unique. There must be a one complex number which will be used as a multiplicative identity in all the set. And similarly, we will discuss the multiplicative inverse for the inverses for each Z in C. Means that is a complex number, C is the set of the complex number. So multiplicative inverses are infinite. And at last we will discuss an important point for eta, which is order relation. Order relation mean can we compare two complex number? This is the order relation. Now if I consider two real numbers, for example 1 and 3, so we can compare these two real numbers. Now you clearly see that 1 is less than 3, or you can say that 3 is greater than 1. Or if you consider two equal number, 1 equal to 1, this is a trichotomy property. If you consider two numbers, two real numbers, for example a, b are two real numbers, so according to trichotomy property, a must be equal to b, or a must be less than b, or a must be greater than b. One of these three must be true for any two real numbers. This property is called trichotomy property. And this equal to, this less than, this greater than, less than or equal to, greater than or equal to are called order relation. So order relations are true in case of the real numbers. You can compare two real numbers. Here you clearly see that 1 is less than 3. This is the comparison. You can compare with the help of this relation that 1 is less than 3 or 3 is greater than 1. So this order relation is true for the set of real numbers. But now the question arises that if I consider two complex numbers, for example 3 plus 4 iota and 7 plus 10 iota, so can I compare these two complex number? Can we discuss that this complex number is greater than this complex number, or this complex number is less than this complex number? This is the order relation. So this order relation, this point will be discussed at the end of the lecture. This is a question that can order relation is satisfied in the set of a complex number or not. So this point will be discussed in the end of this video lecture. So these are the contents for this video lecture. So moving towards the additive identity. What is additive identity? I briefly explain that point, and then we will see to the proper definition for the additive identity. Now if you add if I discussed the additive identity in OR, which will provide the background for this additive identity in C, mean set of complex number. So remember that 0, which is a real number, is additive identity, in R, because if you add any real number, a may be any real number, to the left of 0, or if you add a to the right of 0, you will get again a. Mean by adding additive identity, the number will be not change. You see that a remain the same if you add the additive identity from the left or from the right. You clearly see that the value of a, the value of the real number to which you are adding the additive identity doesn't change. So this is the definition of the additive identity. In other words, this definition in general we can say like this: B is called additive identity. B is called additive identity if B is added with A from left or from right, and you will get again A. Mean you see that by adding B with A from right or from left, the value of A is not changing. A is any real number. So this B is called the additive identity. Now in case of the real number, additive identity is 0, because by adding 0 to a number, that number is not changed when you add 0 from left or right. So in case of the real number, additive identity is 0. Now you know that 0 can be written as 0 is equal to 0 plus 0 iota. So this complex number is the 0 is a complex number, because this can be written in the form of a plus b iota according to the definition of a complex number. So this 0 plus 0 iota is the additive identity. This is the this is the additive identity in C, because if you add any complex number to this from left or from right, that complex number will remain the same. There will be no change in that complex number. So you see, this is the definition. For example, if I say let's say a plus b iota is my complex number, belongs to set of a complex number, and I'm saying that c plus d iota is my additive identity, So now if this complex number is my additive identity, then according to the definition, if I add this additive identity to the right of my complex number, or if I add this additive identity to the left of my complex number a plus b iota, you will get a plus b iota from both cases, because additive identity does not change the given number to which they are adding. So this is the definition of additive identity. So for the case of a complex number, additive identity is 0 plus 0 iota. This is the additive identity. So now you see to the definition. For the set of real number, additive identity is 0. For the set of a complex number, additive identity is 0 plus 0 iota. The definition is, if you add anything, any number with the additive identity, the original value, the original form of that number will be not changed. Either if you add that number to the left of the additive identity or to the right of the additive identity. So by adding 0 to the left or the right to any real number, you will get again that real number. So that's why 0 is the additive identity in the real numbers. And when you add any number, any complex number with 0 plus 0 iota from left or from right, so that complex number will be not changed. So that's why according to the definition, 0 plus 0 iota is the additive identity for the set of complex number, and additive identity is always unique. Just 0 plus 0 iota for all complex number. Infinite numbers, complex numbers are infinite. So for all those infinite complex number, additive identity is 0 plus 0 iota. So remember, additive identity is always unique. Now you see to the proper definition, a complex number c plus d iota is called the additive identity of a complex number a plus b iota. So this a plus b iota is your complex number, and you say that c plus d iota is my additive identity. So if this c plus d iota is your additive identity, then if you add this c plus d iota to the left of the complex number or to the right of the complex number, the original form of the complex number will be not changed, because you say this c plus d iota is my additive identity. So when you add the additive identity to any complex number from left or from right, this is from the right, this is from the left, the value, the form of that complex number will be not changed. So note, 0 complex number, which is 0 plus 0 iota, is the additive identity, because when you add 0 plus 0 iota to a complex number from right or from left, you will get that complex number. So remember that additive identity is always unique, and for the set of a complex number 0 plus 0 iota, which is a 0 complex number, is called the additive identity. So additive identity 0 plus 0 iota is a unique for all complex numbers. That is 0 plus 0 iota is the additive identity for every complex number. So this is the additive identity. Now moving towards the additive inverse. What is the additive inverse? The second content of this video lecture. Now I am moving towards the additive inverse. What is the additive inverse? Additive inverse, additive inverse. So remember, first of all, I am talking about the set of real numbers. Let's say you know that 0 is additive identity NR. This is notation for the set of real numbers. Now let's say A is any real number. A is any real number. So and B is also a real number. So if I add these two numbers, if A is added with B from the left, or B is added to the left of the A, and you get 0, mean you get additive identity. Additive identity. When you add two real numbers and you get additive identity, so they two numbers are called the additive inverses. For example, if I add 4 plus minus 4, so from this I get 0. Or if I add minus 4 plus 4, so from this I get 0. So you see that when I add 4 with minus 4 or minus 4 with 4, so I get additive identity. So whenever you get additive identity in a result when you add the numbers, so those numbers are called the additive inverses, and for each and every number there is different inverse. For example, 4 and minus 4 are the additive inverses. 5 minus 5 are the additive inverses. If I write 1 by 2, so what is the additive inverse of 1 by 2? So if I add minus 1 by 2, so you will get 0. So this minus 1 by 2 is called the additive inverse of 1 by 2, or you can say that 1 by 2 is the additive inverse of minus 1 by 2, because from the addition of these two you get additive identity. So whenever you add two numbers and you get the additive identity, so those two numbers are called the additive inverses. So remember that additive inverses is different for every number. For in this case you see that the additive inverse of 4 is minus 4, the additive inverse of 5 is minus 5, the additive inverse of 1 by 2 is minus 1 by 2, because by adding 4 with minus 4 you get 0 additive identity. For additive inverses you will see that when you add those numbers you will get additive identity. This is the definition. So you clearly see that additive inverse is different for additive inverse is different for every number. Additive inverse is different for every number. So this is for the set of a real number, in a set of real number. So now we know in the set of a complex number that 0 plus 0 iota is additive identity. So when you add two complex number A plus B iota and C plus D iota, and you get additive identity 0 plus 0 iota, so then these two complex numbers are said to be additive inverses, because from their addition you get additive identity. So if I write 1 plus 4 iota, So their additive inverse will be -1 -4 iota, because from the addition of these two you get additive identity. So you see that for this complex number this is the additive inverse, or for this complex number this is the additive inverse. So if I change this complex number 3 plus 4 iota, so -3 -4 iota will be the additive inverse, or for this complex number this is the additive inverse. So you clearly see that for every number there is a different additive inverse, but additive identity is unique. So this is the additive identity. So whenever you get additive identity from the addition of two complex number, so those two complex numbers are said to be additive inverses. Remember, additive inverse for every number is different. So this is the additive inverse. So you see to the proper definition, additive inverse of a complex number. A complex number c plus d iota is called the additive inverse of a complex number a plus b iota if you add this complex number, if you add this with the right of this, or if you add this with the left of this, you will get additive identity. So whenever from the addition you get additive identity, then those complex numbers are said to be additive inverses. Now important note, two complex numbers a plus b iota and c plus d iota are said to be additive inverses for each if we get additive identity 0 plus 0 iota from their addition, which I already explained. This point I already explained. Now every complex number has its own additive inverse, which I already explained. That is, additive inverse is not unique. You see that the additive inverse of a plus b iota is minus a minus b iota, because from the addition you get 0 plus 0 iota additive identity. You see that 5 minus 3 iota is the additive inverse of minus 5 plus 3 iota, and vice versa. Mean minus 5 plus 3 iota is the additive inverse of 5 minus 3 iota, because from their addition you get additive identity. So this is additive identity and additive inverse. Multiplicative identity and multiplicative inverse is similar. For the case of real number, one is multiplicative identity, mi mean multiplicative identity, because if I consider let a belongs to R, be any real number, so 1 multiplied by a or a multiplied by 1, you get a. So this one is called multiplicative identity. When you multiply 1 to the right of a or to the left of a, the original form of a doesn't change, you get again a. So this is the multiplicative identity. As you see in the case of the additive identity, that when you add a number to a given real number, you get again that real number. Mean when you add 0 with a, you will get a. So that's why 0 is called additive identity. So the same definition is here. When you multiply a number with a real number a and you get the same real number, that original real number, then that number which you multiply with a is called the multiplicative identity. So for the case of the real number, 1 is the multiplicative identity, and this multiplicative identity is unique. This is for all. For every number, 1 is multiplicative identity. Now if I define the multiplicative identity in general, so B is called the multiplicative identity for a real number, a if a multiplied by b, b multiplied by a is equal to a. So you see that when you multiply b with a or a with b, mean when you multiply a to the left of b or b to the right of or a to the right of b, and you get again a, mean that real number doesn't change by multiplying b with that. So this b is said to be multiplicative identity. So in case of the real number, multiplicative identity is 1, because by multiplying 1 to any real number, that real number doesn't change. So that's why multiplicative identity is unique. So this is the multiplicative identity for the set of real number. In the case for the set of a complex number, multiplicative identity is 1 plus 0 iota. This is a complex number which is known as the multiplicative identity of a complex number. This is the multiplicative identity. when you multiply any complex number with this 1 plus 0 iota, that complex number doesn't change. For example, if I multiply a plus b iota with 1 plus 0 iota, so I will get a plus b iota. Or if I multiply this complex number from the right, so I will also get a plus b iota. So this is the definition, that when you multiply two complex numbers and you get again that complex number, so this mean by multiplying this to this complex number doesn't change. So this is called the multiplicative identity. In case of the complex number, 1 plus 0 iota is the multiplicative identity. In general, the definition of the multiplicative identity is c plus d iota is said to be multiplicative identity if a plus b iota multiplied by c plus d iota or c plus d iota multiplied by a plus b iota is equal to a plus b iota is equal to a plus b iota. I mean, by multiplying c plus d iota from left or right, the complex number doesn't change. So this c plus d iota is called the multiplicative identity. But for the case of the complex number, 1 plus 0 iota is such a complex number which multiply with any complex number from left or from right, so that complex number doesn't change. So this is called the multiplicative identity. Remember, multiplicative identity is unique. This is for all. This is for all. So now you see to the proper definition. Okay, I am switching towards the proper definition. Now you see, a complex number c plus d iota is called the multiplicative identity of a complex number a plus b iota if a plus b iota multiplied with c plus d iota from right or from left with that complex number. You are multiplying c plus d iota. In the above definition, you say that this is my multiplicative identity. So if you multiply this multiplicative identity to a complex number from right or from left, you will get again that complex number. Mean multiplicative identity doesn't change that given complex number. So you see that when you multiply, so in case of the complex number, that multiplicative identity is 1 plus 0 iota, because when you multiply 1 plus 0 iota from the left or from the right to a complex number a plus b iota, you can get that complex number. You can verify this very easily. Now if I want to verify this is too much easy. Let's say I take 3 plus 4 iota and I am multiplying 1 plus 0 iota. So you see that 3 will be multiplied with 1 plus 0 iota, then 4 iota will be multiplied with 1 plus 0 iota. This is called horizontal multiplication. 3 multiplied by 1 3 multiplied by 0, so this is 0 iota. 4 multiplied by 1, this is 4 iota, and this will be 4 multiplied by 0 iota multiplied by iota square. So 0 multiplied by iota square means 0 iota square is minus 1 multiplied by 0, you will get 0, and 0 iota means 0, nothing, so you will get 3 plus 4 iota. Or if you multiply this from the left to this number, you will get again 3 plus 4 iota. So that's why according to a definition, this 1 plus 0 iota is called multiplicative identity. Now moving towards the multiplicative inverse, a very important. Now you see to this additive identity for the complex number is a zero complex number. Now we discussed that 0 plus 0 is the additive identity in C, and 1 plus 0 iota is the multiplicative identity in C. This additive identity is a zero complex number, and this multiplicative identity is called unit complex number. Unit complex number. Now moving towards the multiplicative inverse. Now the definition will be the same. Additive inverse is when you add two numbers in case of the real and you get additive identity. So these two numbers are called the additive inverses. This is for the real numbers. And for the complex numbers, if you add two complex number and you get additive identity, so those two complex numbers are called additive inverses. So now multiplicative inverses. If I multiply First of all, I am discussed that multiplicative inverse, and remember that multiplicative inverse for each and every number will be different. Mean multiplicative inverse is not unique. Multiplicative inverse. So first of all, I am discuss this for the set of real numbers. Let's say if I take 1 by 2, so if I multiply 2 with this, so you will get 1. So this is my multiplicative identity. So you see that from the multiplication of these two numbers, I get my multiplicative identity. So according to the definition, when you multiply two numbers and you get multiplicative identity, then those two numbers are said to be multiplicative inverses. So that's why I am saying the multiplicative inverse of 1 by 2 is 2, or the multiplicative inverse of 2 is 1 by 2, because from their multiplication I get the multiplicative identity. This is the multiplicative identity in the set of real numbers. So in general, the definition will be, if I multiply two real numbers and I get the multiplicative identity, this one is multiplicative identity instead of real number, then these two real numbers are said to be multiplicative inverses. Then A, B, these will be multiplicative inverses. Multiplicative identity, this one is actually my multiplicative identity. I is also, identities also start from I, and inverse also start from I. So sometime I am writing mi for multiplicative identity and sometime multiplicative inverse, so that's why I write the full identity here. Okay, so this is the multiplicative inverses, because from the multiplication you get multiplicative identity. Now shift this concept to the complex number. Now you know that 1 plus 0 iota is the multiplicative identity in the complex number. So if you multiply two complex number, a plus b iota is one complex number, c plus d iota is another complex number. So if you multiply a plus b from the right or from the left, and from this multiplication you get multiplicative identity, then you can say that this c plus d iota is called the multiplicative inverse of a plus b iota. Let's say this is an important definition. Once again I am repeating this definition. I am finding the multiplicative inverse of a given complex number a plus b iota. This is my given complex number. Please focus on this definition. This is my given complex number. This is my given complex number, and my target is to find out, to find the multiplicative inverse for a plus b iota. So remember, multiplicative inverse will also be a complex number. So according to definition, let's say I say that, let's say this is my given complex number, and I choose that let c plus d iota is the multiplicative inverse of a plus b iota. So if c plus d iota is my multiplicative inverse, so then according to the definition, a plus b iota multiplied by c plus d iota will be equal to 1 plus 0 iota, or c plus d iota multiplied by a plus b iota will be equal to 1 plus 0 iota, because c plus d iota is your multiplicative identity, multiplicative inverse. So whenever you multiply to a multiplicative inverses, you will always get a multiplicative identity. So that's why from this multiplication I get the multiplicative identity. So if my original number is a complex number a plus b iota, and let c plus d iota is my multiplicative inverse, so if this c plus d iota is my multiplicative inverse, then from the product you will always get multiplicative identity. Whenever you multiply multiplicative inverses, you will get multiplicative identity. As I discussed for the case of a real number, 1 by 2 and 2 are the multiplicative inverses. So that's why you will get 1, mean multiplicative identity. So F.Sc plus d iota is the multiplicative inverse of a plus b iota, then their multiplication must give the multiplicative identity. Now the question arises that what will be the complex number c plus d iota, which is the multiplicative inverse for a complex number a plus b iota. So now going towards the proof. So the proof is, this is a very simple, but remember I am writing just in formal way now. Let c plus d iota is the multiplicative inverse of a complex number a plus b iota. Therefore, according to the definition, a plus b iota multiplied by c plus d iota will be equal to 1 plus 0 iota, because this is the multiplicative inverse of this complex number. So whenever the multiplicative inverses are multiplied, you will always get multiplicative identity. Now the target is to find out the c and d, mean what will be the value of c in term of ab and what will be the value of d in term of ab. So our target is find c and d in terms of a and b, because the given complex number is a plus b iota. For example, it is given that 3 plus 4 iota is a given complex number. So what complex number is multiplied with this to get 1 plus 0 iota? Now let's say I multiply c plus d iota and I get 1 plus 0 iota. So this c plus d iota is called the multiplicative inverse. So if you are finding the multiplicative inverse of a number, you need such a number that when multiplied with that original, you get multiplicative identity. So I am in search for c and d in terms of a and b. Here I consider a specific values of a and b. So that specific value of a and b will be given, and c and d will be known to you in terms of a and b. So you will just plug these values in place of a and b in the expression of c equal to that and d equal to that, and you will get that complex number, that multiplicative inverse. So is okay the page is running to loose. Okay, so this a plus b iota multiplied by c plus d iota is equal to 1 plus 0 iota. This c plus d iota is the multiplicative inverse. So if I multiply this, so AC plus AD iota, horizontal multiplication, BC iota, BD iota square is equal to 1 plus 0 iota. So this is AC, this iota is equal to minus 1. So this will be minus BD, and this is AD plus BC iota is equal to 1 plus 2 iota. So this is a complex number, this is a complex number. So you see that there is a equality between these two complex numbers. So according to the definition of equal complex numbers, AC minus BD will be equal to 1 and AD plus BC will be equal to 0. So from here you see that AD is equal to minus BC, implies that D is equal to minus BC divided by A. So put this value here in place of D. So this implies that AC minus B into minus BC divided by A equal to 1. So I am finding the value of C first. So this is AC plus b square c divided by a equal to 1, taking the LCM. So this will be a square c plus b square c and divided by a, so equal to 1. So this is taking common c, so this is a square plus b square, okay, and shift one on a on the right, so it will be in the multiplication because here it is in the addition. So c will be equal to a divided by a square plus b square. So this is the value of c. This is the value of c. Now put this value in d. So d will become, put this value in d. So d will become minus b by a. The value of c is a divided by a square plus b square. So this a will be cancelled with this a, and d will be minus b divided by a square plus b square. So this is the value of d. So the complex number, this is the value of d. This is the value of c and this is the value of d. So if c plus d iota is multiplicative inverse of given complex number a plus b iota, then c will be equal to a divided by a square plus b square, and d will be equal to minus b divided by a square plus b square. So in short, the multiplicative inverse, now we say that c plus d iota is my multiplicative inverse for a plus b iota. So this implies that c is actually equal to a by, actually c is equal to a by a square plus b square, and d is equal to minus b by a square plus b square. So that complex inverse, multiplicative inverse will become a divided by a square plus b square plus minus b divided by a square plus b square iota. So this is the multiplicative inverse for a plus b iota. This is the multiplicative inverse. So whenever you multiply a plus b iota with a divided by a square plus b square plus minus b divided by a square plus b square iota, you will get multiplicative identity, either if you multiply this from the left or from the right. In ordered fair form, you know that a plus b iota is equal to ab. So this is a complex number. So a divided by a square plus b square plus minus b divided by a square plus b square iota. This will be an ordered fair form, will be written as a divided by a square plus b square comma minus b divided by a square plus b square. So if a complex number is given in the ordered fair form, so their multiplicative inverse will be a divided by a square plus b square comma minus b divided by a square plus b square. Now I consider example 3 plus 4 iota is my given complex number. This is the given complex number. Find the multiplicative inverse for 3 plus 4 iota. So I am comparing this 3 plus 4 iota with a plus b iota. So this implies that a equal to 3 and b equal to 4. So if this is my complex number, so this is my multiplicative identity. So in this case, multiplicative inverse will be a divided by a square plus b square plus minus b divided by a square plus b square iota. So a is 3 divided by 3 square plus 4 square plus, and b is 4, so minus 4. This is a square plus b square iota. So this is 3 divided by 9 plus 16, 25. This minus multiplied by plus, so you will get minus 4 divided by 25 iota. So you see that this is my complex number, which is the multiplicative inverse of this. If you multiply these two complex number, you will get multiplicative identity.
If you multiply, so verify this, if you multiply these two complex number, you will get the multiplicative identity. So this is the multiplicative inverse. Okay, and now I will show you a proper definition for the multiplicative inverse. Okay, so you see that. Okay, now see this multiplicative inverse of a complex number. A complex number c plus d iota is called the multiplicative inverse of a complex number a plus b iota. If you multiply this multiplicative inverse from right or from left, you will get multiplicative identity. That is, two complex numbers are said to be multiplicative inverses of each other if their product gives the multiplicative identity. So the multiplicative inverse of a plus b iota is a divided by a square plus b square minus b divided by a square plus b square iota, because when you multiply these two complex number, you will get multiplicative identity. This is also the verification, and I also do prove this, that how this is the multiplicative inverse of this, and this is also a verification. You see that when you multiply the multiplicative inverses, you get multiplicative identity, and this is the from left or from right. So you clearly see this. Find the multiplicative inverse of this. So the value of a is minus 2, the value of b is minus 3. So just put these values in this, so you will get the multiplicative inverse. So this is the multiplicative inverse. Now you see that this is the ordered fair form of the multiplicative inverse of a comma b. Now important point for the eta, which I said in the beginning, that I will give you a point which will be very important for eta, order relation in the complex number. Complex number possesses all the properties that real number possesses. We discussed the different properties for the set of complex numbers. We from the previous lecture, you know that all these properties, closure property, commutative property, associative property, distributive property, are hold in the set of a complex number, which is also hold in the set of real numbers. But in the set of a real number, order relation is also defined, which I already explained at the beginning of the lecture, that when you consider two complex number, so you can compare these two complex number. One is less than 3, you can say the relation between the in case of the real number. You see that 1 and 3 are real numbers, and you clearly mention that 1 is less than 3. Now if I consider two complex number, 3 plus 4 iota and 7 plus 10 iota, so can I say that which complex number is greater or which complex number is less than the other complex number? No, the order relation does not define in the set of complex number. You cannot say that this complex number is greater or less than this complex number. Remember, the order relation is not defined in the set of complex number. Mean you cannot say that one complex number is greater than the other complex number or not. So this is the important point for eta. So you see that important point, the complex number possesses all properties that the real number possesses except the order relation. That is, we cannot say that one complex number is greater than the other complex number and vice versa. Mean one complex number is less than the other complex numbers. Also see to the properties of the conjugate and modulus of a complex number. So z absolute is equal to minus z, which can be also equal to z bar absolute, which is also equal to minus z bar absolute. Double bar of the z is equal to z, mean double conjugate will give you again that original complex number. You can do this by own. When you multiply complex number and its conjugate, you will get the absolute square of that complex number. Z1 plus Z2 whole bar is equal to Z1 bar plus Z2 bar. This is equal to Z1 divided by Z2 whole bar, mean conjugate, is equal to Z1 bar multiplied by Z2 bar mean conjugate. Z1 divided by Z2 whole bar mean when you divide Z1 by Z2 and then take the conjugate, or if you take the conjugate of the Z1 and Z2 and then you divide, you will get the same result. In this case, you see that if you add two complex number first and then take the conjugate, or if you take the conjugate first and then add, the result will be the same. If you multiply the complex numbers first and then take the conjugate, or if you take the conjugate first and then multiply, the result will be the same. So these properties will be also used in the exercise for the verification, and these are also important for the eta. Now the sum of two conjugate complex number is real. If you add two conjugate complex number, now a plus b iota and a minus b iota are the conjugates for each other. So when you add these, the imaginary parts will cancel, because when you are taking the conjugate, you change the sign of the imaginary part, so that's why you will get a real. So remember this. The product of two conjugate complex number is also a real. When you multiply two conjugate complex numbers, a plus b iota and a minus b iota are the conjugate complex numbers of each other, so you will get real number. A, b are real, so their square and addition must also be a real. So also remember this. Okay, so this is the important. So result number 3, when the sum of two complex number is real and their product of two complex numbers is also real, then the complex numbers are the conjugate of each other. Mean when you add two complex number and you get a real number, or if you multiply two complex number and you get a real number, so note that those two complex numbers must be the conjugate of each other. This is the all about this lecture. Inshallah, in the coming lecture we will discuss the exercise questions of 1.2.